Chapter 7, Entropy. Okay, class, today we are going to talk about something very interesting called entropy, and I promise I will explain it like telling a simple story. Let's imagine you have a box of colorful balls. At the start, you neatly arrange them by color. Red balls here, blue balls there. Everything looks nice and organized. But then you shake the box around and the balls get all mixed up. This is like entropy. Entropy is a way to measure how messy or mixed up things are. The more mixed up the balls get, the more entropy you have. Now, remember how we talked about energy? The first law said energy cannot be created or destroyed. The second law, which we learned before, said energy moves from hot to cold, like your tea cooling down. But there's more. The second law helps us introduce entropy, and entropy tells us not just where energy moves, but how energy gets more spread out and less useful. For example, when your room gets messy, it's easy for it to happen naturally, but it's hard to make it tidy again without work. There's a famous rule called the Clausius Inequality. Think of it like this. If you keep track of heat coming in and out of your system and divide it by temperature, and you make a loop like running in circles, you'll always end up with zero or something less than zero. This helps us realize that entropy is like a bank account of disorder. Every time we do something like heating, cooling, or running engines, this account grows. One fun fact is entropy is different from energy because entropy is not conserved. Energy stays the same in the universe, but entropy just keeps growing. So when you see something getting messy, that's the universe following the rule of increasing entropy, like your room, or your hot soup cooling down, or your ice cream melting. Let's talk about how we measure entropy. If you heat something in a very gentle and reversible way, you can calculate how much entropy changes using the formula change in entropy equals heat divided by temperature. Easy, right? So if you heat 100 joules into something at 100 Kelvin, you increase the entropy by 1 unit. Then there's something called the increase of entropy principle. This is a very important rule. It says that in an isolated system where no heat or mass goes in or out, the entropy always increases or stays the same. Like when you pop a balloon, the air spreads out and it never goes back into the balloon on its own. Entropy increases and things become more random and mixed up. Now, sometimes we have special processes where entropy stays the same. These are called isentropic processes. Imagine you have a water slide and the water flows down with no friction, no splashing, no heat lost, just perfect smooth movement. This is like an isentropic process. Engineers love these processes because they are the best-case scenario where no energy is wasted as disorder. We can use diagrams like TS diagrams, where T is temperature and S is entropy. When you see a straight-up line, it means no change in entropy, and when you see curves, it shows how much heat is being added or removed. It's like looking at a map to see how your energy is behaving. On a microscopic level, entropy is about how molecules move. In solids, molecules are packed tight and barely move, so low entropy. In gases, they run around crazy and random, so high entropy. That's why steam has more entropy than ice. When you melt ice, you increase entropy. When you boil water into steam, you increase entropy even more. More movement means more disorder. Finally, entropy isn't just in machines or food, it happens everywhere, even in your life. A clean room turns messy, people get tired after work, energy spreads out, and everything tends to get more chaotic unless you work hard to put things back in order. Entropy helps us understand why no machine can be 100% efficient and why the universe is slowly moving toward more disorder. But don't worry, engineers like us use this knowledge to make engines better, fridges cooler, and power plants more efficient. That's it for today. Remember, energy stays, but entropy always likes to party and spread out.